This video covers part 2 of section 3.2, Proving Existential Statements. We're going to start by talking about surjective functions. In the previous section, we defined a function from a set A into a set B. The set B is called the codomain for the function. For each element A in the domain A, the element B equals f of A is called the image of A under F. The set of all images under F is called the range of the function f. So we can visualize the function by the diagram shown. So for each element A in A, f maps it into an element B equals f of A in the codomain B, and the range is a subset of B consisting of all the images. In general, not every element in B will be the image of an element in A, in which case the range is properly contained in the codomain B. However, in the case that the range equals the codomain, so that every element of B is the image of an element in A, the function is called surjective. So here's the formal definition. A function f from A to B is called surjective, or is said to map A onto B, provided that for every element B in B, there exists an element A in A such that f of A equals B. Or in symbolic form, for all B in B, there exists an A in A such that f of A equals B. To visualize what it means for a function f from A to be surjective, let's start with an element B in the codomain B. The function is surjective provided that there exists an element A in the domain that maps into B. That is, for which B is equal to f of A. The definition of surjective is one of the most important definitions associated with functions and comes up in pretty much every area of mathematics. So it's important that you have a good understanding of the definition and of how to show a function is surjective, as well as how to show that a function is not surjective. For our first example, we want to show that the function f from R into the interval from 5 to infinity, defined by the formula f of x equals x squared plus 5 for each x in R, is surjective. Now note the domain for this function is R, and the codomain is the interval from 5 to infinity. And recall that the interval from 5 to infinity is the set of all real numbers y such that y is greater than or equal to 5. In symbolic form, to show that f is surjective, we need to show for all y in the interval from 5 to infinity, there exists an x in R such that f of x equals y. It's critical when proving a function is surjective to put the domain and the codomain of the function in the correct places in the symbolic form. According to the definition, f is surjective provided that for all y in the codomain, which in this case is the interval from 5 to infinity, there exists an x in the domain, which in this case is the set of real numbers R, such that f of x equals y. The element in the codomain comes first and has a universal quantifier. The element in the domain comes second and has an existential quantifier. Switching either the quantifiers or the sets results in a different and incorrect statement. Now back to the proof. So we need to show for all y in the interval from 5 to infinity, there exists an x in R such that f of x is equal to y. This is a universal statement, so we start with a proof by arbitrary element. We'll suppose y is an arbitrary real number in the interval from 5 to infinity. And we need to show there exists an x in R such that f of x equals y. Since we're now proving an existential statement, we set up our two columns. So we need to find an x and then verify that x satisfies our two conditions. The domain, x is supposed to be a real number, and the propositional function, which is f of x equals y. Now to find an x, we need a real number x satisfying the propositional function f of x equals y. Since f of x is x squared plus 5, then x must satisfy x squared plus 5 equals y. Solving this equation for x, we obtain x squared equals y minus 5, so that x is going to be plus or minus the square root of y minus 5. Now we can choose either the plus or the minus sign. So for instance, choose the plus sign so that x is equal to the square root of y minus 5. So we've now found our x, and so we're ready to move over into the right-hand column. And we can say that since y is in the interval from 5 to infinity, then y is greater than or equal to 5, so y minus 5 is greater than or equal to 0. Since y minus 5 is greater than or equal to 0, then it tells us that x, which is the square root of y minus 5, will be a real number. Now for the propositional function, we can substitute our x equals square root of y minus 5 into the formula for f of x, and we obtain f of x is f of the square root of y minus 5, which will be the square root of y minus 5 squared plus 5, which is y minus 5 plus 5, which is equal to y. So x satisfies the propositional function. So this proves our existential statement. There exists an x in R such that f of x equals y, and thus f is surjective. To visualize what's going on in this proof, we can look at the graph of the function, which is a parabola opening upwards with a vertex at 0, 5 on the y-axis. The domain R of f corresponds to the entire x-axis, while the codomain corresponds to the interval from 5 to infinity on the y-axis. According to the definition, f is surjective, provided that for any y in the codomain, the interval from 5 to infinity on the y-axis, there exists an x in the domain, the x-axis, for which y is equal to f of x. We can also see from the graph that this will be true. Now suppose we change the codomain of our function from the interval from 5 to infinity to the set of real numbers r. So we want to look at the example. Suppose f from r to r is defined by the same formula, f of x equals x squared plus 5 for each x in r. And the question is, what happens if we try to show that it's surjective? To show that f is surjective, we would need to show for all y in R there exists an x in R such that f of x equals y. So for the proof, we suppose y is an arbitrary real number, and we need to show there exists an x in R such that f of x equals y. To prove this existential statement, we set up the two columns. So we need to find an x and verify that x satisfies our two conditions. And to find an x, we need a real number x satisfying the propositional function f of x equals y, which is x squared plus 5 equals y again. And as before, we can solve this equation for x to obtain x squared equals y minus 5, so x is plus or minus the square root of y minus 5. And so just as we did in the last example, we'll choose x to be square root of y minus 5. Now we need to verify that x satisfies our two conditions. And in the previous example, we had supposed that y was greater than or equal to 5, which implied that x, which is the square root of y minus 5, was a real number. In this example, since we only know that y is in R, we don't know that y minus 5 is greater than or equal to 0. So we cannot conclude that x, which is square root of y minus 5, is a real number, because y minus 5 could be negative, and then we'd have a negative underneath the square root. At this point, the proof fails, since we cannot verify that x satisfies the domain condition. Now, just because our proof that f is surjective fails, we cannot conclude that f is not surjective. If we try, but are unable to prove a statement, it doesn't follow that the statement is false, only that we are unsuccessful proving it. Now let's prove that f is not surjective. So for this example, we want to show that the same function that we had before, f from r to r, defined by f of x equals x squared plus 5 for each x in R, is not surjective. To show that f is not surjective, we need to show that the statement, for all y in R, there exists an x in R such that f of x equals y, is false. To show this, we need to show that the negation, which is there exists a y in R such that for all x in R, f of x is not equal to y, is true. So this is an existential statement, so we start by finding an example y. So we need to show there exists a real number y such that for all x in R, f of x is not equal to y. Start by setting up two columns. So we need to find a y, and then verify that y satisfies our domain, which is y is in R, and the propositional function, which is for all x in R, f of x is not equal to y. So we have for any real number x, x squared is greater than or equal to 0. So our function f of x, which is x squared plus 5, will be greater than or equal to 5. Since we want a y for which f of x is not equal to y, this tells us that we should choose a real number y less than 5. We can also see this from the graph of the function. For instance, we can choose y equals 1. So now we've found a y, and we're ready to move over into the right-hand column. And for our domain, clearly y equals 1 is a real number, so there's really not much to say there. And for the propositional function, we need to show that y equal 1 satisfies for all x in R, f of x is not equal to y. This is a universal statement, so to prove this, we suppose x is an arbitrary real number. Then x squared is greater than or equal to 0. So f of x equal x squared plus 5 is greater than or equal to 5. And therefore f of x is not equal to 1, so the propositional function holds. And this proves the existential statement, and thus f is not surjective. Next, we want to look at a more complicated type of function. Let R squared be the set of ordered pairs xy, where x and y are both real numbers. And we'll define f from R squared to R by f of xy is equal to x times y plus 2 for each ordered pair xy in R squared. So this is a function of two variables, and it's mapping our ordered pair xy into just a real number. And we want to show that f is surjective. Now note that the codomain for f is R, while the domain is R squared, so the symbolic form to show that f is surjective is going to be for all z in R, there exists an ordered pair xy in R squared, such that f of xy equals z. Now we need to choose a different letter for the variable in our codomain. We can't use x or y since they're already taken, so we can pick any letter we like, and so in this case I've chosen z. So we're ready to start the proof. We'll suppose z is an arbitrary real number, and we need to show that there exists an xy in R squared such that f of xy equals z. That is, we need to show there exists an ordered pair of real numbers xy such that f of xy equals z. We're again proving an existential statement, so we set up our two columns. So we need to find an ordered pair xy, and then we need to verify that xy satisfies the two conditions. The domain is xy is going to be in R squared, and the propositional function is f of xy equals z. Now our ordered pair xy must satisfy the propositional function f of xy equals z. And since f of xy is xy plus 2, xy must satisfy the equation xy plus 2 equals z. And this can be rewritten as xy equals z minus 2. Now we can pick any two real numbers x and y that satisfy this equality. For instance, we can choose x to be z minus 2 and y to be 1. So our ordered pair xy is z minus 2, 1. So we now have our ordered pair, and we're ready to move over into the right-hand column and do our verification. And we can say that since z is in R, then x equals z minus 2 is in R. Then our ordered pair xy, which is z minus 2, 1, is going to be in R squared. And for the propositional function, substituting xy equals z minus 2, 1 into the formula for f, we obtain f of xy is f of z minus 2, 1, which will be z minus 2 times 1 plus 2, which is just going to be z. So xy equals z minus 2, 1 satisfies the propositional function. This proves the existential statement, and thus f is surjective. So the procedure in this example is pretty much the same as the procedure in the earlier example, just that the function is a little bit more complicated since it's mapping ordered pairs into real numbers as opposed to just a real number into a real number. Next, we want to talk about elementary number theory briefly. Number theory is a branch of mathematics concerned, at least at the elementary level, with the properties of the integers, and more particularly with the properties of the positive integers or natural numbers, 1, 2, 3, and so on. It's one of the oldest areas of studies in mathematics, with important results dating back to ancient times. In fact, its name is due to the ancient Greeks, for whom the word number meant positive integer and nothing else. The following is a fundamental definition from elementary number theory. An integer b is divisible by an integer a not equal to 0, which is denoted by a and then a vertical line, b, provided that there exists an integer k such that b is equal to ka. In symbolic form, b is divisible by a provided that there exists a k in z such that b is equal to ka. Now this notation, a with the vertical line b, is read a divides b. Now this should be interpreted as a divides into b evenly. In the case that b is not divisible by a, we use the notation shown. We put a little slash through the vertical line. For our first example, we want to show that negative 12 is divisible by 3. To show this, we need to show there exists a k in z such that negative 12 is equal to k times 3. So if we choose k to be negative 4, since k equals negative 4 is an integer, and 12 is equal to negative 4 times 3, then we can conclude that 3 divides into negative 12, or negative 12 is divisible by 3. For an example involving a proof, we want to prove for all non-zero integers a divides into itself. This has symbolic form for all a not equal to 0, a divides into a, where the domain for a is a set of non-zero integers. This is a universal statement, so to prove it, we use a proof by arbitrary element. We suppose a is an arbitrary non-zero integer, and we need to show a divides a. To prove this, we need to show there exists a k in z such that a is equal to ka. This is an existential statement, so we set up two columns. So we need to find a k and then verify that k satisfies our two conditions. Well, since k must satisfy the propositional function a is equal to ka, we choose k to be 1. And for our verification, clearly k equals 1 is an integer. Not much to say there. And since a is equal to 1 times a, which is ka, then the propositional function holds. And this proves the existential statement, and thus a divides a. So this is a very simple proof. We're going to finish this video by discussing very briefly non-constructive proofs of existence. So far, all of our examples have been constructive proofs of existence. The second method of proving an existential statement is a non-constructive proof of existence. This involves showing either A, that the existence of an example x for which the propositional function p of x is true is guaranteed by an axiom or another theorem which has been previously proved, or B, that the assumption that no such example exists leads to a contradiction. We'll consider proof by contradiction in a later section. For right now, we want to do one example that illustrates a non-constructive proof of existence of the first type. We first need some definitions. So let S be a non-empty set of real numbers. A real number little m is an upper bound for S, provided that S is less than or equal to m for every S in S. For our second definition, again, let S be a non-empty set of real numbers. A real number capital M is the least upper bound of S, provided that 1, capital M is an upper bound for S, and 2, M is less than or equal to little m for every upper bound little m of S. So capital M as a least upper bound means that it's first off an upper bound, and secondly, it's the smallest of all the upper bounds. So it's exactly what its name implies. We also need an axiom of the real numbers. The completeness axiom of R states that every non-empty subset of R, which has an upper bound, has a least upper bound. The completeness axiom, as its name implies, is an axiom which we assume is true about the set R of real numbers. As an axiom, it does not require a proof itself. So now we want to use the definitions and the completeness axiom to prove that the set S, which consists of sine of 1 radian, sine of 2 radians, sine of 3 radians, and so on, has a least upper bound. So for the proof, we want to apply the completeness axiom, and to do so, to apply the completeness axiom to prove that the set S has a least upper bound, we need to show that S is non-empty and has an upper bound. Well, the set S is clearly non-empty. We can see that it contains elements. And since sine of x is less than or equal to 1 for all x in R, then for all elements S in S, S is less than or equal to 1. So every element in S has the form sine of x for some x. So this tells us that 1 is an upper bound for S. So now since S is non-empty and has an upper bound, then the completeness axiom tells us that S has a least upper bound. And that proves what we want it to. Now note that the completeness axiom guarantees that the set S in the example has a least upper bound, but it doesn't tell us what the least upper bound is. A good guess for the least upper bound would be capital M is 1, which is actually the case. It's not especially easy to prove that m equal 1 is the least upper bound, however. In any case, if we're only interested in proving the existence of a least upper bound, we don't need to determine its value. And this is typical of non-constructive proofs of existence. We're able to conclude something exists, but we may not know what it equals.